Merci. Bienvenue, bienvenue au séminaire informatique. Aujourd'hui, on a Megan Peters en Californie. What time is it in California right now?
It's 7:30 in the morning.
I'm really grateful to you for doing that. The Chinese people have a lot more against them when we do this.
Sure.
La conférencière est Megan Peters de l'Université de Californie à Irvine. S'il vous plaît, taisez-vous maintenant parce que c'est enregistré. S'il vous plaît, ne parlez pas. Please do not speak. À l'Université de Californie à Irvine, sa conférence est la confiance, la métacognition et le problème difficile de la conscience. On connaît déjà le problème difficile à partir de la conférence de David Chalmers qui a eu lieu ici. Je lirai son résumé. I'm only going to read the abstract in French because everybody else should already have seen it. Le sentiment conscient, le ressenti, on aurait dit, le problème difficile reste un défi central pour les sciences cognitives. Cette présentation explore si les modèles computationnels de la confiance métacognitive et de l'incertitude ancrés dans la psychophysique introspective et les représentations d'ordre supérieur peuvent éclairer l'expérience phénoménale. What I just said was that famous one that we're going to see whether metacognitive confidence, uncertainty, somehow anchored in psychophysics, introspective psychophysics, can help solve the hard problem. I've spoken enough. Megan says that if there are questions, s'il y a des questions de compréhension, vous pouvez poser pendant sa conférence, sinon ça sera 50 minutes. So if you have questions that require clarification for understanding, you can ask during the presentation. Otherwise, it'll be after the talk, which will be 50 minutes. Welcome, Montreal, Megan, virtually, and it's yours.
Thank you so much. It's truly my pleasure to be here, even though it is 7:30 in the morning. That's totally fine. This is normal for me. So thank you so much. I'm really pleased to be here. I'm terrifically excited to share some of the work that we've been doing with you. And I'll preface this by saying, I'm not sure that we're going to solve any hard problems today, but I hope that it will be an interesting discussion nonetheless, and that maybe we can take some steps towards that solution, or maybe even deciding that we don't need to solve it at all. So with that, let's just go ahead and get started. So as I mentioned, as Stephen mentioned, I'm joining you here from California. So my daily life doesn't look exactly like this, but the palm trees are definitely there. And if I turned my webcam, you would see that this isn't terribly far off. So this, however, is not Irvine. This is actually the corner of Hollywood and Highland. It's right in the heart of Los Angeles. And I'd like you to picture yourself standing at the perspective of the photographer here, right in the middle of the crosswalk. And you're staring westward down Sunset Boulevard towards the coast, towards the Hollywood Hills, and towards here, the sunset. And I'd like you to then, as you're standing there, imagine that I asked you to tell me the color of one of the cars in your visual periphery. Now, this might not work on the screen in front of you because it's quite small, but if you were actually standing here, those cars would be way out here in your visual periphery. And I'd like you to imagine what would happen if I asked you to tell me one of the colors of one of those cars, or perhaps whether one of the people on the sidewalk here is a celebrity. Okay. So if you were standing in that crosswalk and staring straight ahead, this is actually the information that your brain has access to in order to answer those questions. So out here in the visual periphery, your retina barely processes color. Its spatial resolution is really quite bad, but this is not the subjective experience that you would be having. Your subjective experience would look a lot closer to this. This is how you would subjectively feel if you were standing in this crosswalk. You would experience a vibrant, rich, and colorful scene, very much like the one that we started with. So in our work, what we're asking is, why are these different? Why does our subjective experience of seeing not always match the actual information that's being processed by, arriving at actually, our brains? So this is a motivating question that we'll be asking today, is how do we subjectively experience the world? And in our work, we start by building this hierarchy of the system that we're studying. So first, there's a world out there. It has features, it has characteristics, it has contents, it has structure. Presumably, it actually exists and is not just totally an illusion. And the standard widespread cognitive science view that I'm sure many of you share is that we build internal models of that world, and that it is these models that support our cognition and our intelligent behavior. But this isn't the end of the line. We don't just build these models and run them forward and use them to drive our behavior in the world. We can move on to recognizing that we also query those models. We evaluate their contents and quality. And we also evaluate whether the ongoing representation of that model right now is likely to reflect the true nature of the environment, or maybe it's an internally generated hallucination, or maybe it's just noise. So we do this kind of source monitoring exercise as well. And so ultimately, the representations that we build, that we carry around in our heads and that we query and run forward in order to support adaptive behavior in uncertain situations, especially, that they are not only about the state of the world, but they're also about the quality and source of our internal representation. So they're about ourselves as much as they are about the world. Okay. So these here are what we might think of as potentially unconscious, at least to start. So you might argue with me about whether they're conscious or not, but here I'm going to posit that they're the same kinds of representations that a Tesla or even a Roomba might have. It has some sort of internal model of the world about where the chairs are, where the other cars are on the road, if it's a Tesla. And those representations can drive the decisions that we make about how to behave, but they aren't necessarily conscious. At least not yet. And then I'm going to argue that these are the more subjective, conscious evaluations. So this is when your mind might be asking, is my representation of the world good? Is it stable? Is it clear? Is it colorful? Or maybe it's just noise. And so it's these subjective, conscious evaluations that I'm going to be focusing on today. In my research, I'm focusing on these introspective or metacognitive type experiences and the neural representations that support them. And I use a multimodal and interdisciplinary approach that combines behavior, psychophysics, computational modeling, a little bit of neuroimaging and neurobiological approaches, a good chunk of machine learning and AI or artificial intelligence, and then we have a hefty dose of theory and philosophy thrown in. So I'm going to try to cover a lot of ground today. All right. And we're going to do a sampling of some of this work motivated by three major questions in today's talk. So first, we're going to use some behavior, some psychophysics and modeling to ask whether introspection is constant across tasks, stimuli, or situations. So this is introspection and the subjective experience that you have of the world constant if we hold constant the world model that you've built to some degree. Then we're going to take a look at the computations that the brain might be doing. Here, I'm going to get my laser pointer. So we're going to look at the computations that the brain might be doing and where those computations might be housed. So ultimately, it is this squishy piece of wetware that's doing the heavy lifting to a certain extent. And so we want to understand what and how the brain, where and how in the brain that is going on. And then we're going to zoom out and ask about some more theoretical considerations for consciousness, some interfaces between the empirical work and some more philosophically motivated approaches, including potentially connections to or possibly ways to sidestep the hard problem. All right, so first, is introspection a consistent phenomenon? So our approach here is to build on over a century of psychophysics, but to change the focus just a little bit. So traditional psychophysics focuses on building quantitative descriptions of the relationship between stimulus properties and perceptual capacity. So something objective about the world, how much we can discriminate or identify, for example, on the basis of how much physical signal strength is present. like luminance or contrast or intensity of electric shock. So what we're going to do is take this one step further to build what we're calling introspective psychometric functions. And those relate those perceptual capacities, that objective performance ability, to our subjective experiences. So concretely, you can think about this as the relationship between how confident you might feel in a decision or how clearly you think you see the stimulus relative to how likely you are to have identified it correctly to begin with. And doing the introspective psychometric function part is really important because it allows us to control for any unconscious processing and home in to kind of isolate the subjective experience components. So this means that we can use this approach to ask, does subjective experience on the y-axis have a constant relationship with objective performance or processing capacity on the x-axis? Is the shape of this function always the same? And if not, when and how and potentially why does it vary? All right, so a great candidate for absolutely destroying introspection would be blind sight. So this is the neurological condition where damage to early visual cortex can result in cases where patients can use visual information to effectively make decisions or to navigate through the world, but there is no subjective experience associated with their capacity. So think about it this way. Essentially, these patients can actually see, at least to some extent, but they don't think that they can see. So perhaps some of you are familiar with this and you've seen this 1,000 times before in your intro psych classes, but if you haven't, I encourage you to go and look this up because it is a fascinating phenomenon that is a really powerful tool in the study of subjective experience in isolation from objective performance capacity. However, fortunately for everybody, these patients are very rare. There are only a few in the world who have been confirmed to have kind of true blind sight-like behavior. And this means that as psychophysicists, as basic science researchers, we need to find an alternative. We can't just study the patients. We need to find a way to use lab-based manipulations like visual masking, for example, in neurotypical populations to try to induce that blind sight-like behavior so we can end up with N of more than 1 or 2. So in the experiments that we ran that I think some of you read a paper about back in 2015, so this is when I was a postdoc with Hak-Wan Lau, we showed a paradigm that looks like this to typical college-age students. We would show a target in one interval and we would mask it with a forward-backward masking paradigm. So here the target is an oriented Gabor patch. This one is tilted left from vertical. And show mask, mask, target, mask, mask. And your task is to tell us what the orientation of the target is. Was it tilted left or right from vertical? Then we show you a target that is physically not there. And you do the same thing. Now, we don't tell you it's not there. So we show you mask, mask, nothing, mask, mask. But we don't tell you that there is no target present. And we say, you still have to tell us whether the target was tilted left or right from vertical. Okay. And then we ask, which of these two intervals did you subjectively experience with more confidence? Which one do you think you saw better? So we did multiple experiments that they all kind of had this same flavor. And this is why we have this target absent interval, because it sets a floor on the subjective experience. So controlling for everything else in the experiment, all of the masking, all of the timing, everything, you should have no additional target-related subjective experience if there is no physical target. So this is the only thing that changes between the intervals. And of course, everything is counterbalanced. Sometimes this interval is first, sometimes this one's first. Okay. All right. So to evaluate if this manipulation actually created blind sight-like behavior, what we're going to do is plot the objective performance capacity when there is a target there. Okay, so in the target present interval, how often do you get it right, left or right tilt? And then if the masking successfully disrupted subjective experience, when we plot subjective experience on the y-axis against this, we should see something that looks like this, where there is some degree of ability to do the task at like these low contrast levels for the target, but there's an introspective blindness. There is subjectively doing the task when the target is present is no different from doing the task based on nothing at all. Okay, so this would be introspective blindness or blind sight. So this is what we're looking for if masking produces blind sight-like behavior, like everybody in the literature prior to this paper said that it did. Okay, well, spoiler alert, it didn't in this paradigm. So instead, what we found was that as soon as people could tell the identity of the target when it was there, they could tell us that they introspectively felt more confident in that choice than when the target was physically absent. And this went against all previous reports that masking could induce blind sight-like behavior, because it showed that even when you can just barely see enough to identify the target stimulus, you subjectively experience something different than when the target is physically absent. And this conclusion was also bolstered by some modeling work that we did. This is a Bayesian ideal observer model. I won't go into the details here for the sake of time, but the idea here is that this model is predicting behaviors in the same kind of paradigm as the human subjects went through. And so it predicts these behaviors either on the based on the probability of having made a correct response in a two-interval forced choice or two-alternative forced choice, or just on a pure visibility signal. And they fit the data equally well, and they both fit the data quite well. So this told us that masking may not, in fact, alter the relationship between objective performance and subjective experience, which again is against how people think that masking had worked in the past. Okay. So because masking maybe wasn't a strong enough manipulation, we did it again with TMS, and this time we're TMSing early visual cortex. So this is another manipulation that is supposed to induce blind sight-like behavior in neurotypical adults. So we zap you in the back of the head when we show you a target, and this induces an artificial temporary scotoma in a localized area of your visual field. So this time, though, we didn't just not see blind sight. I've changed the x-axis a little bit here, but it's the same kind of thing. We have performance on the x-axis and subjective experience on the y-axis. And so even though the TMS did actually make people worse at the objective discrimination task, it did actually make them see that oriented target less well in terms of their ability to discriminate its orientation, it paradoxically made them feel more confident. So you can see that the intercept of these two lines, both the model is the black line and the humans are the red line, both of these deviate from kind of the intercept that we would expect at 0.5, which would be no objective performance capacity and 50-50 betting. So that would be akin to this 50-50 line that we expected here. Now we did the modeling again. This time the Bayesian ideal observer model actually failed to predict humans' data, but we did do an alternative model, which we called an introspectively blind model. It actually got it right, and that is the model that I'm plotting here. I won't go into the details here, but this model is going to come back later on in the talk, so keep that in mind, and we can talk about the details more in the Q&A if you want. Okay. But for now, we're going to stick with just pushing on the heterogeneity of introspection. So, then we thought, well, we've done masking, we've done TMS. What about just simple stimulus manipulations? Let's just mess with the stimulus a little bit. So here, in this paradigm, the stimuli are these random dot kinematograms. They're randomly moving dots. They take up the whole screen. It kind of looks like a little snowstorm on your computer screen. And we can change the density of these dots so that sometimes that snowstorm on your computer screen looks like flurries, and sometimes it looks like a blizzard. And so that's what we're going to call the low versus high density conditions. The task is very simple. So sometimes on one side of the screen, to the left or to the right of this fixation cross in the center, the dots move coherently downward like a little waterfall. And participants have to tell us on every trial which side, left or right, has the little waterfall and rate their confidence. And the red circles are not on the screen for the participant. They're just there to show you now for the purposes of illustration. All right. So we then make the same introspective psychometric functions as before. And now we're building a new summary statistic that we've been developing, which we're basically just coloring in underneath those introspective psychometric functions to get kind of a combined threshold across all possible objective performance capacities that are shared between two comparison conditions of interest. So this allows us to measure the degree of subjective experience over the same range of performance capacity for all conditions. So again, we're controlling for that objective processing capacity and isolating the subjective experience bits. So literally what we do is we just take the integral of these curves. We take the area under the curve. Okay, so if we do that, the patterns are actually very clear. Now I'm plotting the area under each of these functions for each of these conditions for the low, medium, and high densities. So this is flurries, kind of medium snowstorm, and blizzard. And what we can see very clearly is that more dots on the screen means you feel more confident in your decision introspectively, even though it doesn't actually make you better at the task. So more dots did not make you better. Didn't change your performance capacity at all because we're controlling for that in the analysis. But more dots just makes you feel more confident. Okay. We can also see whether attentional manipulations do something interesting. So now we're switching gears from stimulus to attentional manipulations. And so here what we're doing is we're manipulating attention to targets that we're presenting peripherally out here in your visual periphery. So these are in the far corners of a computer screen that we're using. And we're using cueing. So the targets that will show up on every trial are these oriented Gabor patches embedded in noise on some of the experiments, or they're these little ovals that show up in this figure ground stimulus here. And you can kind of see this one's horizontal and this one's vertical. And here the Gabor patch is tilted to the right, and here it's tilted to the left. Okay, so on every trial, you get this central cue that says, pay attention to one of the four corners of the screen. You have to keep your eyes focused on this fixation cross, and then you would direct your attention to one of those four corners. And then after the targets are presented, we show you a response cue. And the response cue can match the pre-cue. So we say, pay attention here, and then actually respond, tell us the orientation of the target and how well you think you saw it. Or the cues can be invalid. So pay attention here, just kidding, actually respond over here. Okay, and we do the same kind of analysis, the same kind of objective versus subjective, and take the area under the curve, get some bar plots, and what we see is this. So now we see paradoxically that when you're not paying attention, so that's the red bars, to that target in the visual periphery, you stop paying attention, you feel you can see better than you ought to across a matched range of performance from the valid attended case. So remember, this is controlling for performance capacity. So yeah, invalid attention makes you worse at the task, but we control for that in the analysis, and we say then over the range of performance that is matched between invalid, neutral, and valid, attention cues make you worse at identifying the target, but they don't make you enough worse at thinking how well you can see to correspond to or account for how much worse you actually got. Okay, so you actually got more worse than you think you did, if that makes sense. So, and finally, in this section, an additional wrinkle is that whether you report feeling more or less subjective confidence can also depend on why you're computing or reporting confidence to begin with. So in this project, we examine whether the loss function that the observer is trying to minimize would make a difference in introspective or confidence reports. This is a pure math and simulation project, but the punchline here is that there's a very big difference in confidence behaviors if the observer is trying to, for example, maximize the reward they get for saying high confidence when they're right and low confidence when they're wrong, versus when they're trying to calibrate their confidence reports to their accuracy. Like here, to be able to say, I'm 75% confident when they're 75% likely to be correct. So what all of this means is simply that the way an observer reports subjective confidence under varying conditions, so maybe like some of the ones we've been talking about and some of the manipulations we've done, that can reveal insights into the decision policies that they're using to compute confidence. Okay. All right, so this is what I just said. Shifts in confidence depend on the policy that the agent is using to report confidence, and we can discover the observer's policy that may help understand their behavior better. Okay, so this is the end of the first section. And what I've shown you is just across a few studies here, there's a very clear pattern that we think is emerging. Introspection is not constant across conditions, across tasks, and so on. We are seeing this variation in the relationship between your ability to do some task, which is this world model thing, and your subjective experience. So something is going on here in the building of these internal representations at the higher level that isn't just a direct readout of the first order representational content. So now we want to ask why. What is it that the brain is doing in building these higher order subjective experiences that allows for this variation? Why is this happening? So we're going to move on now to ask, what is the brain doing when it's doing introspection? So we'll talk about first the theme that we've been discovering across TMS, dot density, those attention cues that I showed, the other manipulations that I actually haven't shown you here. We're seeing that, generally speaking, if there's higher evidence, there's more stuff on the screen, or there's higher noise, like when you zap with TMS, or you're looking at stuff in your visual periphery, like these ones, or you don't pay attention, that's higher noise too, you end up feeling more confident than you kind of ought to, given how well you are performing the task. And we, again, also see that this lines up with the example we started with. Noisier signals out there in the visual periphery are not accompanied by an appropriate drop in your subjective feeling of visual clarity. Okay. And we've also seen that these patterns are kind of hard for standard Bayesian ideal observer models to account for. I showed you a little teaser about the fact that I had to build an introspectively blind model in order to account for those TMS results. So this prompts us to think of some alternative computations that might give us some traction for understanding this confirmation bias in the subjective experiences that we've seen. So because we've been calling this a confirmation bias, we can think of this as when that confidence or subjective experience is depending too much on the amount of evidence that your brain has collected that supports the decision that you made. And it's relatively insensitive to evidence suggesting that you might have been wrong, including any extra noise. So when I ask you to report how confident you feel, or when your brain is computing that, it's saying, how much evidence do I have that I'm right? Never mind the evidence that I might have been wrong. So some more support for this confirmation bias idea also came from this ECOG study that we did back in 2017. So here we're decoding signals directly from the surface of the cortex in awake behaving humans. These are patients undergoing surgery for intractable epilepsy. And the idea here is that they're doing kind of this face house judgment task and then rating their confidence. And again, without going into too many detail, what we see is that we can extract evidence of the choice that you made through this decoding step. So on every trial, we can extract the pure face evidence and the pure house evidence that the participant used in order to drive a decision and potentially a confidence judgment. From these decoders, what we found is that using Bayesian ideal observer and signal detection theoretic models, we found that, again, it was evidence supporting your decision. So basically, like if you said face on a given trial, that's the evidence that was supporting your confidence judgment, not the combination of face and house evidence. It was that face and house evidence that drove your decision. You picked the bigger one. Face evidence is bigger than house evidence. Okay, you're going to generally pick face. But then how much evidence you had supporting your decision is what drove confidence. So the decisions were driven by this balance of evidence approach, face minus house or house minus face, and confidence was driven by your confirmatory evidence. So now we need to figure out how this dependence on decision congruent evidence might occur in something that we can call biologically plausible circuitry. So here we've built an evidence accumulation computational model. This model has two kinds of units: those that accumulate evidence for each possible choice alternative independently, like face or house. So these are kind of self-recurrent units that you'd find in a leaky competing accumulator model, for example. These two units kind of don't inhibit each other, so the amount of house evidence that you've accumulated has no bearing on the amount of face evidence that this unit has accrued across time. And then we also have these kinds of units that compute the difference in the amount of evidence that the system has accumulated for each, which we're going to call green relative evidence or differencing units. And these are the ones that compute how much face evidence there is over house evidence or vice versa. So in this project using simulations, we showed, that if you read out confidence from the yellow or absolute evidence units and drive these into what we call confirmatory evidence, that the model can reproduce even highly complex versions of this confirmation bias, that it can actually create versions of this more dots equals higher confidence over the same range of match performance, for example. Okay. Right. And so now we're wrapping up testing this model in brains directly, because ultimately, again, it is this squishy piece of wetware that's doing the heavy lifting. We don't want to just build simulations and hope that they're right. So we've developed an approach for finding these kinds of absolute and relative evidence kinds of units at the voxel level, in posterior parietal cortex. And we're going to see how they behave when people are doing these kinds of decisions plus confidence judgment task. So based on what we've been describing, the more a voxel contains these yellow absolute evidence kinds of units, the more it should covary with confidence judgment. So we should see that if we have like a way of computing, we're calling this voxel inhibition tuning, we have a way of computing kind of how much a given voxel in posterior parietal contains these absolute versus relative evidence units. And the yellower a voxel, the more it should be driven by, or the more it should covary with or drive those confidence judgments, because that's how we built the model. So this is a prediction, and this is in fact pretty much exactly what we're finding. So we're finding that across 19 of our 20 subjects that we have collected so far, that they are showing a significant fit with our model as opposed to a control model. I don't know what this 20th guy is doing. He's really messing everything up, but everybody else is showing the right effect. So the exceedance probability here is 95%, showing that we really do have good agreement with our model. Okay. All right, so that's the decision congruent evidence input to introspection. But of course, maybe there's other inputs. So again, it's not just a direct readout of that world model. We have additional components building this introspective experience part of the process. So anybody here in the room who has built Bayesian models of perception, that's probably some of you. I can see the audience, so could you raise your hand if you've ever built a Bayesian model of perception or run into it at some point? Anybody? Sort of? Kind of? Okay. So anybody who's built Bayesian models of anything then knows that it's not just the likelihood that matters. It's also a prior, right? We need a prior. We need to understand what's going on here. So the expectations here about environmental properties based on our experience. This is the kind of thing that drives our experience, our perception of orientation or speed or luminance or specularity, the shininess of objects in the world. There's a huge, beautiful literature about Bayesian models of perception going back to basically 1988 or earlier that was built up by a large number of very smart people, but they never pointed it at introspection. And so that's what we're going to do now. We're going to try to understand this prior over expected uncertainty. So these are the expectations we have not only about the environmental uncertainty, which would be kind of a hazard rate prior about the environmental stochasticity, but now this is a prior over our own uncertainty, our own internal noise structure, and how that changes with different conditions, different attentional deployment, and different contexts. So now we can ask, is the expected uncertainty prior also a contributor to subjective confidence? And we first started thinking about this in that TMS study that I showed you earlier. So remember, I mentioned this kind of introspectively blind model. That model is a Bayesian ideal observer. It builds its subjective estimates based on the amount of noise it expects to be present in the system. So what this means is that if TMS injects extra noise, this model is blind to that noise. It just calculates the Bayesian posterior based on the variance that it expects to be there in the generating distributions, not the variance that is actually there after injecting noise with TMS. And with that wrong now expectation, that wrong prior, it actually matches the data quite well. So this gives us a sense that perhaps this degree of expected uncertainty is a driver of those introspective confidence judgments. We actually later followed this up with some more Bayesian and signal detection theoretic simulations. And these show that the degree of confidence you feel out here in the visual periphery, especially under inattention, this can overestimate your task accuracy under specific conditions if you depend on noise expectations and you get those noise expectations slightly wrong. So if the expected uncertainty that you have when you deploy your attention or you get zapped or something is just not quite right, it's a little bit off, that can completely change the degree of confidence that you subjectively experience. And that's due to the prior and not to the likelihood. So how can we get at these expectations about noise so we can test this further? Like this is nice, this is a just so story, but like, how do we get at those expectations? How do we go find those in neural circuitry and understand what they look like? So it turns out that finding those noise expectations is rather hard. Because by definition, anything that we read out from the brain about uncertainty right now, like anything we decode from the brain about the uncertainty of an internal representation, that's going to be the posterior, not the prior. If I try to find it covariating with confidence judgments, I can't decode this thing if I want to get only at this. I'm going to have to find a way of getting at the prior directly. So in this next project, we're going to use an fMRI data set from a decoded neurofeedback study to get at those noise expectations. So let me tell you what decoded neurofeedback does, and then I'll tell you why this is a good approach for understanding this expected uncertainty. All right, so in decoded neurofeedback, the idea is that we're teaching awake behaving human observers to produce target patterns of brain response. So this is beyond just typical neurofeedback where you'd say increase the power in your beta band or your alpha band in EEG, or increase the bold signal in your amygdala or your striatum or something like that. Now we're teaching people how to produce targeted patterns of brain response that go with a particular target neural representation. So for example, I want to teach you to think about red things and not blue things. I can decode red versus blue in V4 or any other color associated region, and I can then use this decoded neurofeedback approach to teach you to produce that pattern. So I put you in the scanner, I read out in real time the patterns of voxel response in the target region of interest. I compare the current voxel pattern to the target pattern that I've found through pre-training a classifier. If they match, I give you a nice big reward. And if they don't match, I give you a small reward. And you, as the observer, receive only the following instructions. Lie in the scanner, try to make the circle as big as possible by thinking about stuff. That's it. That's all you get. If your brain makes the right pattern, I'll give you money. If it doesn't, I won't. And so you have basically no direction. You have no supervision over what kind of pattern you need to be producing. So this is kind of a reinforcement learning approach where your brain is playing Marco Polo and saying like, how about now? Did I make the right pattern? How about now? Did I make the right pattern? Okay. So I'm giving you all this background because we know decoded neurofeedback works empirically, at least sometimes. So people are able to learn how to produce targeted patterns of brain response that go with red stuff and not blue stuff, or spiders and not snakes. So people can actually learn how to do this, but there's controversy and inclarity in how they are learning how to do this, what the mechanisms are and the algorithms that they're using to produce these target neural patterns. All right, now back to the main story. We think that humans may solve this task through learning distributions of expected uncertainty and then minimizing those expected uncertainty distributions in order to reveal the target pattern. This is kind of akin to how humans solve other tasks. They kind of calculate expected uncertainty reduction on the basis of a given motor command, like eye movements, for example, all of Jackie Gottlieb's work, if you're familiar with that. So we constantly calculate, if I do this, my uncertainty will be reduced. And so we think that this is an algorithm that the brain may co-opt in solving this task as well. If I do this, if I change my brain activity in this way, my uncertainty along the task relevant dimension will be reduced and I will reveal the target pattern of interest. So If this is what people are doing, this is a hypothesis. If this is what people are doing, then we could, in theory, build a machine learning approach to doing the same task using reinforcement learning and use that to get at those distributions of expected uncertainty. So this is, in fact, exactly what we've done. We built a denoising diffusion model, which learns about distributions of noise in order to reveal a target pattern. Typically, a denoising diffusion model is going to learn to produce images of cute cats. We're going to, this is the basis for early, like DALL-E, if you ever played with generative AI, like diffusion models, like the early image noise, early, like 4 years ago, image generation models. But now we're going to use them not to produce images of cute cats, we're going to use them to produce voxel patterns of brain response. And in learning how to do this task, the model learns a distribution of expected uncertainty in its own voxel patterns, which we can then manipulate, use, do all of the tricks to understanding neural representations on. And what we find is that individual differences in these expected uncertainty distributions can actually explain how well people can do the decoded neurofeedback task. So there are certain groups of people who do better at this decoded neurofeedback task than others. And until this project, we didn't have a good understanding of where those individual differences are coming from, why some people can learn how to do this and others can't. There was a hypothesis put forth that people who have better metacognitive ability might be better at decoded neurofeedback. And this seems consistent with our approach as well, that those who are better at learning their own uncertainty distributions may be better at solving the decoded neurofeedback task. All right, so what's becoming clear now is that subjective confidence seems to overweight confirmatory evidence. This shows that confirmation bias that we've just talked about. And we also think it takes as input these expectations about uncertainty or noise. So we're developing some kind of new methods to go find those in the brain. All right, so in the last couple minutes now, we're going to take a zoom out and say, well, why are we doing all of this? This is like kind of fun and interesting from a basic science perspective, at least I think so. But ultimately what we want to do is gain a bigger picture understanding. So let's next talk about conscious experience from the theoretical perspective and how all of this research program fits in. So let's think about what introspection is doing. It's kind of building this higher order representation, all of this stuff at the top. And for those of you who are more in the philosophical vein, you might recognize that this is precisely what higher order theories of consciousness are positing is going on in the construction of subjective experience. That introspective computations, that kind of inward-looking evaluation of the first order representational content, structure, stability, and so on. It's those computations at this higher order level that are the reason that we become consciously aware of something. Now, this is more like A consciousness or access consciousness than it is P consciousness, but I think phenomenal consciousness, but I think that we're moving in the phenomenal consciousness direction by doing introspective psychophysics, by characterizing the way, quantitatively, the way that the subjective experience varies with all these manipulations that we're doing while holding some aspects of those first order representations constant so we can isolate or tease apart the higher order from the first order. So in some recent work, I actually suggested a practical way to build on these higher order theories with what I called this metacognition as a step towards explaining phenomenology approach. The idea here is that introspection or metacognition it's really well suited to helping us understand those subjective experiences because it rests on targetable neurocircuitry. As I've shown you, we can go in and manipulate those neural circuits. We can understand what they're doing. It offers a powerful computational approach, as I've been showing you, through supporting the development of these computational models, some of which are ideal observers, so we can understand loss functions and normative behavior, some of which might be more heuristic, but we can still get at it with computational approaches. And also because it produces these subjective experiences beyond just objective perceptual capacity. You can imagine that I'm not particularly interested in doing psychophysics on a Tesla, but I am interested in doing psychophysics on you guys at the higher order level to understand your subjective experiences beyond your kind of Tesla abilities to understand the world around you. And this is essentially the approach that I have been describing, just far. And so, in fact, this project that I previously described, this attentional manipulation project, if you recall, with these little ovals that are horizontal or vertical, this is now going to ask, do we even need those higher order representations? So I kind of propose that we do, and higher order theories propose that we do need those higher order representations to understand subjective experiences. But this, again, is a hypothesis. So we can test that. We can say, are first order representations enough? So a specific variant of these first order theories proposes that it's the strength of local recurrent activity in early visual cortex, that's sufficient to explain subjective strength. So that's why we're using these figure ground stimuli. And it turns out you can put people in the scanner and you can measure the early visual cortical response when there is a figure present, so in this case, but then you can rotate the texture inside that figure exactly 90 degrees and the figure completely disappears. And so this would be called a figure absent condition. And the idea is that both of these drive feed forward activity equivalently, but it's only the recurrent feedback activity that makes that figure pop out. And this has been shown with electrophysiology in humans and in monkeys and so on. So we can measure this in fMRI. We can show you figure present, rotate the texture 90 degrees, show you figure absent, measure the early visual cortical response. We get something that looks like this. So we get, as the lines get longer and longer, short to long here, we can see that the early visual cortex activity changes across time. It shows this center surround activity, and that is specifically the recurrent activity that is driving this kind of pop out effect, this experience that you might have of seeing this oval. So first order theories propose that is the strength of this figure ground recurrency, this figure present minus figure absent signal, that is sufficient for explaining subjective experience strength. So if we put that on the x-axis, we can ask, is there a monotonically increasing relationship? If so, first order theories might be all that, first order representations might be all that you need. But if there is not a monotonically increasing relationship between this first order recurrency signal and subjective experience, then maybe those higher order representations and higher order theories are necessary after all. In another project that we've just started, we're looking at those higher order representations themselves. So now we're doing this in the context of reality monitoring, which is the ability that your brain has to tell the difference between perception and imagination, how it tells the signals came from outside in the world or the signals, the call is coming from inside the house. Okay, so this is a critical capacity of your brain, as we previously mentioned. Deciding whether the internal model is of the world or an internally generated hallucination is a really important thing for the brain to be able to do. You don't want to be mistaking hallucinations for reality. Now, there are actually multiple variants of these higher order theories, and they all make different claims about what exactly those higher order representations are doing in this reality monitoring context. So higher order state space theory, for example, says vividness is all you need. If you have a very vivid imagined experience, you might actually mistake it for a weak reality or weak perceptual signal. So vividness and reality monitoring are the same information. It's the same dimension. Reality monitoring just uses vividness. That's what higher order state space theory says. Perceptual reality monitoring theory, in contrast, says no, vividness is one dimension, reality is another. So you could, in theory, have an extremely vivid imaginary experience that you would never, ever mistake for reality. Okay, so because there's multiple variants of these higher order theories, we're trying to tease apart what is the nature, dimensionality, and maybe decision policies applied to those higher order representations. So we put people in the scanner, we have them, and we show them images that are kind of degraded so that the vividness is kind of similar between perception and imagination. And then we have them look at objects and rate how vivid they are. And we have them imagine objects and rate how vivid they are. And then the idea is that we're going to use a machine learning technique, which is called domain adaptation. This is a way of statistically aligning the representations or distributions from two different domains. So here we'll take all of the brain data from the perception runs and all of the brain data from the imagination runs, and we'll statistically align them so that a classifier on the machine learning side should not be able to tell the difference between perception and imagination. And then we can ask, is vividness still present? Can we still get a vividness signal out of these statistically aligned representations? If yes, then perceptual reality monitoring might be right. And if no, higher order state space might be right. And there's a bunch of other nuances to this project, and I'm happy to go into more details, but that's kind of the basic idea. Okay, so the last couple things I'll say here is that, recurrent processing theories and higher order theories, they're not the only games in town. There's a whole zoo of these computational functionalist theories. They all posit that, performing computations of the quote unquote right kind is necessary and sufficient for consciousness. Now, the cynical reality is that probably none of these theories is right, even the ones that we're targeting in the projects that I just talked about. But they still can be useful in developing scientific questions like those projects, and they can help us to drill down, I think, into what kinds of computations we think are giving rise to subjective experiences at all. So regardless of your favorite theory, we can ask what consequences these theories might have and the empirical manipulations might have on subjective experience and our theories of that. And we can also ask, which we did in this paper, what consequences these different theories might have for subjective experiences, potentially in other systems like artificial intelligence. And I'll just briefly do a self-important advertisement, which is if we want to keep pushing on this computational approach to understanding consciousness, we also need to train people to do this right and with the kind of most modern approaches in mind. So this is why I designed and created the last day of NeuroMatch's newest summer school intensive course. This is the Neuro AI course. And the last day is called Mysteries. It kind of hangs out here separate from the rest of the course. And we focused here on consciousness and neuroethics. So in the first year alone, we've taught hundreds of students about access versus phenomenal consciousness and consciousness versus intelligence, how they're not the same thing. There's hands-on coding exercises implementing some simulations inspired by several of these theories. So if you haven't decided to participate in NeuroMatch just yet, that's fine. I don't blame you, it's very intensive. But if you just want to go and have a look at some of the materials, you can find all the materials online for free, and you can go and have a look at this day if you're interested. And so I had help from a great number of really smart people, including very luckily the late great Dan Dennett, who provided a small lecture for us in this lesson. Okay, so that's basically all that I have for you today. I have a little bit of a few things that I've talked about for kind of the future. But I think that I will stop there because we're a little over time and we can take some questions. So I'll just wrap up by saying, I hope that this research program is going to help answer the question I posed at the start. It's also going to help develop new research programs and educational opportunities so that answering this question might only be the beginning. But I hope that I've convinced you that maybe understanding introspection or metacognition, its behavior, its computations, might give us a handle on something about subjective experiences that allows us to at least step away from or put to the side for now the hard problem of consciousness. So I'm going to stop there and we can have a nice discussion. Thank you very much. And everyone there is muted, so I cannot hear anything that you're saying if you are talking.
Can you?
There, that's better.
Hello?
Thank you.
You can hear me? Okay.
Yeah.
How come you heard me when it all started and then you stopped hearing me when you started to talk?
I'm not sure.
Okay.
I'm not sure. If you were trying to interrupt me throughout, then I apologize.
No, I wasn't. No, I wasn't. What I want to ask is, what do you mean? I don't want to immediately jump to what it is that you said you don't want to talk about, but well, what do you mean by phenomenal experience?
Yeah, so I use there the classic definition that Tom Nagel put forth as something that it is likeness. And I'm interested in trying to isolate the way that we can report on something that it is like from the objective performance capacity. Now, I fully admit that the qualitative character of phenomenal experience that Tom Nagel, that Dave Chalmers, that others have pushed on, that the folks who are developing integrated information theory are trying to push on, that the phenomenal experience component of the something that it's like is not something that any of the program that I've shown you here today could get at. That's the qualitative nature. That's the hard problem of consciousness. What I'm hoping is that by trying to characterize through these self-report measures in introspective psychophysics, the unique contributions to reported subjective experiences, that we're going to build this multidimensional understanding of how subjective experiences are constructed, how they change with different contexts, and how they maybe vary across individuals as well. And so this is actually, I would love to add to, does anyone here know about Anil Seth's perception census that he ran? This big, massive global survey basically about like, you know, is the experience that you have of the world similar across tons of different people? I want to add metacognition and these kind of introspective judgments into that. And so I'm trying to convince Anil to do that in the next iteration of the perception census, to understand that individual difference. And I think, I'm hopeful that if we do that, that this kind of ineffable, personal level aspects of the phenomenal experience that we have from the philosophical angle, that those may not dissolve, but they may become antiquated labels for things that we then have much better handle on. So just like we called life this kind of magical property that, you know, we couldn't quite put our finger on back when we were first studying life, we now have decomposed life into its constituent parts, and it's now like much more tangibly and much more objectively describable by different kinds of biological properties that a system does or does not have. And so I'm kind of hoping we're going to go there, and that phenomenal experience as the, you know, ineffable, qualitative, qualia containing subjective components, that may kind of become a less useful label over time.
Forget about the ineffable stuff, okay? I asked you what phenomenal experience was, and actually the first thing that you said that has a reference point was Tom Nagel's "What is it likeness?"
Yeah.
Now I have to ask you what is it likeness? What makes, now I'm not going to get philosophical, what makes Tom Nagel's statement, "What is it like to be a bat?" makes sense? But if Tom Nagel had said, "What is it like to be a stone?" it wouldn't have made sense. What's the difference?
I think that my go-to answer for this would be something like the supposition on my part that in order for there to be something that it's like, you need to be a creature or an entity or an organism or agent that has something akin to a mind. And that if there's no information processing present, that there is nothing that it is like to be that entity. This is in contrast to the folks who are panpsychists who would say, no, it totally makes sense.
Wait, sometimes what you say drifts off. You said, what was the thing that you said? There's something, it's like the what? And then I heard the word mind. What were you actually saying?
Oh, that you're a creature or an agent that has a mind.
Sounds like we're asking the same question.
Well, I don't think that
now having a mind has taken over the role of first phenomenal consciousness and then what is it likeness?
I'm not sure we are.
Let me put it on something that is less philosophical than that. I think that the reason we asked that about a bat, which happens to be alive, and a stone, which happens to not be alive, isn't that there's something about being alive versus not being alive that's having a mind, and we're back to when we have no idea what we're talking about. It is because if you kick a stone, it doesn't feel a thing. Don't kick bats.
How do you know that the stone doesn't feel a thing?
What Tom Nagel could have said that was less enigmatic was not what is it like to be a bat, but what does it feel like to be a bat? And the missing component in a stone is that it doesn't feel.
According to, I mean, I totally agree with you. I don't think that there's anything that it's like or anything that it feels like to be a stone. There are people who would disagree with you, though. And the panpsychist approach is actually growing in number.
Yes, yes, you're right. And how can you live in the United States without realizing that there isn't a thing that some people believe? Okay, are there any, what I encourage other people now to do is either out in Zoom land or here, is to just raise your hand if you have a question or a comment. Unless you want to keep hearing me ask all the questions. Et puis vous pouvez poser des questions en français, je les traduis. Vas-y.
Hi, Megan. I don't know if you hear.
I can hear.
Thanks for being with us today. It was very interesting. I would be, though, very much interested to know what are your targeted future researches you aim to do on the subject, and in what way, if ever you began to go on the field, this could be applicable in the future on some domains with some organizations, helping people doing what? I mean, from an applicability perspective, did you begin to think about that, or is it too early?
That's a great question. So I skipped these slides because I didn't have time, but I can pull them up and show you very briefly what our future plans look like. I had them prepared. So there's some other stuff that we're doing here. We're basically, kind of pushing on like a large whole-scale approach to understanding how we can influence introspection. And this includes some aspects of the practicality that you mentioned. So this last one here is a much more practically focused study. The idea is that we are studying the relationship among introspective or metacognitive capacity, perceptual and memory capacity, and the locus coeruleus or norepinephrine circuit in an aging population, a healthy aging population. And the reason that we're wanting to do this is that the locus coeruleus norepinephrine circuit is one of the components that tends to break down in the healthy aging process, that locus coeruleus circuit integrity can degrade across time, and that individual differences in the degree to which this degrades might have very real impact on not only people's perceptual and memory performance. This is the arousal system, by the way. This is the system that says, hey, pay attention to something when something new happens, right? It gives you like a squirt of noradrenaline kind of throughout your brain that changes the signal to noise ratio of how your brain is encoding information. And it drives like, the difference between expected versus unexpected uncertainty and source monitoring of that kind of environmental volatility tracking and so on. So if your brain is not doing a great job at monitoring noise and monitoring uncertainty, and it gets worse with aging, then it might be not just that you get worse at perceiving things, your reaction time gets worse, your memory gets worse, that kind of thing, but also the meta level components become worse. So you become worse at seeing, but you don't know that you become worse at seeing. Or you become worse at remembering, but you don't know how much worse you have become at remembering. And what does this have to do with the norepinephrine circuit? And then this is also implicated in a number of neurodegenerative diseases and so on. So this is a basic science project, but the idea is to understand this circuit. So there's that. We also have, let's see, I'll skip some of this other stuff. This is a more kind of practical approach project here. Again, we're using this decoded neurofeedback, but now we're using it to causally manipulate those voxels that I mentioned that are like absolute versus relative evidence. This is a project that's actually funded by the Air Force Office of Scientific Research. Again, basic science project, but the idea is that if we understand the computations that are giving rise to this potential confirmation bias in confidence, we might be able to undo it or make it worse, right? So we might be able to understand how to manipulate stimuli or create training paradigms to help people calibrate their confidence better to match their task accuracy. And metacognitive training is a kind of complicated space in the literature. There's some early work that says, yes, you can totally train people to be metacognitively more accurate in their perceptions. And then there's some later work that said, no, that work had confounds, and it's kind of a little bit of a mess. So we proposed this project to the Air Force to say, we need to understand the basic neural circuitry here, because if you're the Air Force, you would want to train people to watch a video screen and be really well calibrated to know exactly what they're seeing and how well they can actually read that screen as well. Such that if that screen were manipulated in some way, imagine a drone footage feed. You're an Air Force guy, you're driving a drone around. You need to know not only what you're seeing in the drone's video feed, but how confident you are that you're seeing correctly. And so this is something that we think has very practical benefit for, yeah, the military, but also for like doctors in like learning to do perceptual learning to read medical x-rays or like or MRIs, that kind of thing. So those are some of our future projects that have a more practical benefit or approach. This one I won't talk about too much. If you want to come see this project, we'll be at SFN in November. The idea here is to look at how introspection and statistical learning come online together. So as you learn about the structure of the world and you build an internal model, does your ability to query your internal model also come online at the same pace, or does it lag behind? And so this has implications for how that introspective or metacognitive assessment interacts with the learning process. We know that if you make a prediction about what's happening in the world and you're highly confident about that prediction, and then something completely different happens, you might update your internal world model very much more than if you made a prediction about what's happening in the world and you weren't very confident and then something different happened. So confidence and metacognitive abilities, metacognitive efficiency do interact with learning, but we don't know how they come online together. So we're trying to ask that question, and the first behavioral results will be at SFN in November. So there's also, I think, some clinical benefit that might be found. So if we can better understand like reality monitoring, for example, there's some potential approaches or information towards interventions for populations that have trouble with reality monitoring that might be possible. So a classic example would be a schizophrenic population. So these individuals with schizophrenia have trouble with reality monitoring. They mistake hallucinations for reality. And so maybe there would be, through understanding the basic science components of reality monitoring, there would be a way of alleviating some of those really unfortunate and distressing symptoms, positive symptoms in a population with schizophrenia.
Thank you very much.
Did you, I have a question for the questioner. Did you mean industrial applications or human applications?
So, but I was wondering if it was too early to have practical examples of industrial or any kind of other sectors than you said healthcare and military for the time being, or is it too early? Thank you.
So yeah, I think aside from like industrial and military, like I mentioned AI very briefly.
Yeah.
I'm not an AI researcher. We just wrote like kind of an opinion piece about this and how, you know, AI is particularly atrociously bad at metacognition and introspection. There's some new research coming out that says under certain conditions you can kind of train it to be better, but we all know that large language models are just like really terrible at knowing when they're wrong. They're really bad. They don't have this introspective capacity, at least not the way we do. So whether you think this is a good or a bad thing, if we want to build models that know when they're wrong, then reverse engineering it in us could also be a path forward there.
This is a very interesting point because I was questioning myself about the tools you already began to put in place. Could we ever apply them to IA algorithms?
Maybe. There's a paper that it's preprint right now and it's under review that I wrote earlier this year with Mark Stivers. So if you want to, I can find it and put it in the chat, or I can send it around. It's just an opinion piece. It's very short, very like kind of high level, not in the weeds. But basically it's like, what are some of the major differences between the way that humans rate confidence and the way AI rates its own confidence right now in its decisions? But then what are the problems with the fact that those are different capacities for human AI collaboration. So the way AI communicates its confidence to us is it's been trained to like always be very confident, right? It's like, sure, I can totally answer that. And like, here's an answer that I just totally made up. Like that's basically all the LLMs. And so the way that we interact with AI carries with it these biases, where if I interact with you, I assume that you're rating your own confidence something like the way I am, right? You're doing something kind of like maybe like I'm worse at it than you are, but we have kind of the same kind of internal machinery. But AI is totally different. So maybe what we need to do is focus on the alignment problem in metacognitive evaluation in order to help those large language models not only like rate confidence more like we do, and that will help this communication aspect. And I do think that it's something we can do in AI systems. You can ask them about their confidence. You can probe them in different ways. You can actually open them up and look at the uncertainty in their internal representations and how that relates to the confidence that they kind of report to you. And so we can do something akin to some of the work that I've done here in AI systems as well, I think. And there will be more of that in the future.
Thank you.
Okay, last call over there. Yes, go ahead. Could you stand up because then you'll be seen? Ah, yeah.
I raise my
I can see your hand.
You know, you hear me?
Yeah, there we go.
I have a more philosophical question. In your talk, you discussed about metacognition, perception, and decision making mainly. Do you think it's sufficient to explain the hard problem of consciousness? Or do you think about other components and how to model them computationally? Thank you.
I see. So I feel like there's two components to this question. One is my approach sufficient for explaining the hard problem of consciousness? And that's kind of like, are we going to solve any hard problems here with this approach? But then like the nuanced component is, you said other components that maybe I'm not considering, and that would be maybe like embodiment, emotion. Like, could you give an example of the other components that you're thinking of?
Imagination or abstraction. I don't have maybe the good terms.
Okay. All right. That's helpful. So, yeah, I don't think that, I think that the research program that I've laid out has the potential for making good progress on solving access consciousness. How is it that we become aware of our environments? What do we become aware of in terms of our environments and our own internal processes? But of course, there are some things that maybe we will be experiencing that we cannot verbally report. So I've talked a little bit about that. I wrote an opinion piece last year on introspective psychophysics and like kind of the theoretical components of the research program that I've just put forth today, and also its limitations, which is that, maybe there's aspects of our experience that we can't report on, or maybe that our reports belie those subjective experiences entirely. So I think that we will make progress here. My hope is that yeah, the hard problem and the explanatory gap is like way over there. And I don't think that I'm going to be taking like a wild leap and solving that problem with this research program. But I think that I'll bring us closer to where we can see it more clearly, and that possibly the problem will dissolve or change shape as we approach it. And so that I think would be progress. So I'm not going to die on any hill and say my research program is going to solve the hard problem of consciousness. Like, no way. But I don't know that the way that we're formulating the hard problem right now is fruitful for driving empirical lines of research. And I think that as we build those empirical lines of research, that the shape of the hard problem, the nature of the hard problem is likely to change. So as everything does, right? We have a theoretical treatment, and that as we approach it and we gather more empirical data, like our understanding changes, and so the shape of the problem changes. In terms of other things that might be related to or might be missing from this research program, I fully admit that I'm not talking about like symbolic reasoning. I'm not talking about logic. I'm not talking about compositionality, like at least not using those terms. There's an entire beautiful line of research that's about like agentive behavior as needing to be embodied in order to create this internal representation that might have a distinction between self and external environment. And I'm not pushing on any of that in this research program. I think that there's some components of that line of work that would be really valuable to incorporate in the future. So if you're wanting to build a model of the world and you're wanting to build a model of yourself in the world, the model of yourself and your evaluation of your own world model needs to include a component that says, this is my world model, it's not yours. So this self-other distinction will need to come in there. It's not really exactly the same thing as a reality monitoring mechanism. It's more of a source monitoring mechanism. Like, where did this information come from? Where did this model of the internal model come from? And so there's some work in, you know, reinforcement learning agents trained in virtual environments that has this kind of self-other embodiment distinction that I think is useful. And then the other one that comes up a lot when we're talking about phenomenal consciousness or consciousness in general, like whether a person or a bat or a rock can have it, is this idea of biological necessity. So do I need to be a biological organism in order to have subjective experiences? And I'm more on the computational functionalist side, where I think that it is in theory possible to abstract away into computational space and then to reinstantiate those computations in a separate kind of circuitry. We know that multiple realizability and computational level description does work for other things in the brain besides consciousness. So divisive normalization is a thing that we can write down in math, but the biological circuits that instantiate divisive normalization are very different if you look at the fruit fly versus a mammal. And so I don't see why we can't have the same kind of computational level description for some of these capacities that I've been talking about here. Folks like Anil Seth will say, no, we need to have biology, that biology is special. There's only, that there are certain kinds of capacities that only biology can instantiate. And consciousness is one of them. So he and I disagree about that. And there are folks on both sides of that camp. So biology would be another thing that I'm not really considering here.
Okay, all of the views that you mentioned will be represented here, including the ones that you said you didn't cover. There'll be plenty of people who will be talking about the symbolic linguistic sides of this as well.
Yeah, that's great.
But in this case, I just want to thank you for coming here so early in your morning.
It's my pleasure.